As we have already seen, the hydraulic jump allows the flow to cross the critical depth by connecting a supercritical flow with a water depth below HC and a subcritical flow with a water depth above HC. We have also mentioned that significant head losses could occur in hydraulic jumps. We will now calculate these head losses. In this laboratory flume, we have two pitot tubes, one here and one here, that allow to measure the head upstream and downstream of the hydraulic jump. At the upstream side, we have a very small flow depth here below the gate, but we see that the water level in the tube rises up to here, so indicating that the kinetic energy V square over 2G is important. At the downstream side, the water depth is much larger, but the velocity is much smaller, as indicated by the level in the pitot tube again. So we can observe that the difference in head is important. Here, J is the difference in head between the upstream side and the downstream side. This reflects the important head losses induced by the hydraulic jump. So, how to calculate these head losses? Let us assume a rectangular horizontal channel. The head loss J12 between section 1 and section 2 is expressed by this equation. This equation can be developed as indicated in equation 1. We would like to eliminate the discharge from this expression. Therefore, we will go back to a result that we obtained in the previous lesson. Indeed, when developing the expression for the Sequent depth in a rectangular channel, we obtained equation 4 that could be transformed using the definition of the critical depth into this highlighted equation. So the equation we just recalled, linking the two Sequent depths to the critical depth, is written here in equation 2. Using this equation to replace Q square over GL square in equation 1 here, we obtain equation 3, and then equation 4 after developing and grouping the terms. Equation 4 can finally be written like this here. So we have expressed the head losses in a very simple way, using only the two Sequent depths. Moreover, when we look at this equation, we see that H2 has to always be larger than H1 for the head losses to be positive. A negative jump with a depth H2 smaller than H1 is impossible, as it would result in a gain in energy. So, the hydraulic jump always connects a supercritical flow with a depth H1 below HC to a subcritical flow with a depth H2 larger than HC. This very simple expression for the head losses was verified experimentally by the USBR, and we can see that despite its simplicity, it reproduces very well the measurements that are illustrated by the blue points. It is also interesting to represent the head loss as a fraction of the initial head, so H1 minus H2 divided by H1, the initial head at the upstream side of the hydraulic jump. This is indicated by the green curve here, and again we see a very good agreement with the measured points. We can also observe that a stable jump with a Froude number of about 5 leads to a head loss of about 50%, so it dissipates 50% of the initial energy of the flow. This explains the main use of hydraulic jumps. They are used as energy dissipation devices at the end of dam spillways, for example, such as the Stilling Basin illustrated here on this picture. And we see that the flow is very turbulent, there are rollers, many things happen here that induce a lot of head losses. The USBR has designed several types of Stilling basins. One of the most widely used is this type 2 basin, with upstream chute blocks here, and a dentated sill downstream. The purpose is to force the hydraulic jump position here in the basin that is built in reinforced material to avoid damages to the downstream riverbed here by excessive erosion, for example. So the jump has to be located here where the riverbed is reinforced. Another example is the USBR Type 3 basin with intermediate baffle piers used for medium heads. The end sill here forces the bottom jet to detach from the bed, while the intermediate baffle piers break part of the bottom jet. However, such baffle piers can only be used for impact velocities smaller than 15 meters per second, and that's why these are only used for medium head. With a high head, the velocity would be much larger than this 15 meters per second. The stilling basins also reduce the length of the hydraulic jump in such a way that the portion of the riverbed that has to be protected is reduced. We can see in this graph the reduction in length obtained for the two illustrated basins, the Type 2 in blue and the Type 3 in green, compared to the standard hydraulic jump in the red curve here. And we see that instead of 6 times H2, we have a reduced length up to less than 3. So Type 3 basin may divide the length by 2. So, to conclude this lesson, we have seen that hydraulic jumps induce significant head losses that can be calculated in a very simple way. The knowledge of these head losses is essential for the design of stilling basins, which are one of the most important practical applications of hydraulic jumps. See you now in the next lesson. Goodbye.